Hello and good morning also from my side. I'm Sophia, and today I want to talk about new approximations for temporal vertex cover on always star temporal graphs. So this is joint work with Eleni, who's also one of the organizers. Let's see what this title actually means. It's quite long. A lot of you might be familiar with the minimum static vertex cover problem. So this is just when we're given some sort of graph, we want to find the minimum number of vertices such that every edge is covered at least by one of its endpoints. So if we consider this toy application here, we have a museum and we have corridors, and the corridors hold artworks, for example. We might want to place security cameras into the corners. And of course, we want to have all artwork covered and want to place the minimum number of security cameras. So in this toy example, we could select this vertex here and this vertex here, and thereby cover all artwork with the minimum number of cameras. However, often in practice, we don't have a static setting, but things change over time. Maybe not all corridors hold artwork all of the time, or plug in whatever application you want to use. And in this scenario, we can capture this behavior by what is called a temporal graph. So in a temporal graph, we not only have edges and vertices, but we also have a time labeling function, which is called lambda, which assigns every edge a certain number of time labels where it is active. We can also look at this in a snapshot view, where basically in every snapshot, we just display the edges that are visible at the time, or in the underlying graph view, where we just plot the underlying graph and then label the edges with the labels where it is active. And we call the lifetime of such a graph T, which is just the highest label that is assigned. And if we translate this behavior now to the vertex cover problem, we need to somehow cover the edges. But what does that mean in terms of temporal graphs? So we introduce a definition that is called temporally covered. So before an edge was just covered by a vertex, and now it's covered by a vertex appearance, WT. So we need to fulfill two things. First, the vertex W needs to be an endpoint of the edge. And secondly, the edge actually needs to be active at the time step T. So to speak, the vertex appearance VW covers all adjacent edges to W, which are active at time step T. And we can translate this now to the temporal vertex cover problem, where we now want to find a subset of vertex appearances to temporarily cover at least one every edge at least one appearance. So if we would consider this example here, where we take A in the time 1 and C in the time 3, we can see that this is actually not a valid temporal vertex cover, because the edge BD is never covered in a time step where it is actually active. So if we were to include now the vertex B here, then we actually have a valid TVC, because every edge is covered by at least one vertex appearance in a time step where this edge is actually active. However, we can still do a bit better, because instead of taking the B and the C here, we can just use the D at time 2 and thereby create a smaller TVC. And in this case, it's also the minimum size temporal vertex cover. However, you might have noticed that every edge is only covered a single time over the whole lifetime of the graph. If we have repeated monitoring tasks or something like this, it might not be sufficient to do only one coverage over the whole lifetime. And therefore, the sliding window temporal vertex cover was introduced. This allows some sort of regularly monitoring by introducing a fixed size window of size delta. And basically, we just extend our definition so that every edge not only needs to be covered over the whole lifetime, but in every single window. So if we take here, for example, this window of size 2, that would mean that not only, in the first window, we're actually fine because all the edges are covered. However, in the second window now, we see that the edge AB is not covered anymore. So we need to include it include something else, because right now this is not a valid delta equals to sliding window TBC. However, if we were to add, for example, the edge, the vertex appearance A3, then we're fine, and we have created, a valid solution. The problem now is that both the TBC and the sliding TBC have been already proven to be NP-hard. So in practice, it's not very efficient usually to just plug in algorithms. What we do about this is we use certain tools. For example, we use approximation and restriction. What do we mean by that? So if we use approximation, we fix a certain approximation factor, let's say rho or something, and we say every solution that our algorithm creates cannot be worse than this factor rho times the optimal solution. So in some sense, our solution is sufficiently good for the application that we want to use it for. And the other tool is restriction, where we create a smaller problem by just looking at certain cases. For example, we look at temporal graph classes. In general, here we distinguish underlying and always. What does that mean in particular? So basically, we could say we have an underlying path graph structure. So if we look at the underlying structure where we have these labels, then the structure we have is a path. However, in the time steps itself, there might be disconnected behavior here. If we look at, for example, an always degree at most D behavior, that would mean that in every snapshot, we have a maximum degree of D. However, in the underlying structure, again, this degree might be larger. And this toy example here, this is almost always at most degree 2 graph, because in every snapshot, the degree isn't larger than 2. However, in the underlying structure, it's larger. And
so this is 3, right?
Sorry?
So in time step 1, vertex 1 has degree 3, yes? So it's 3 versus 4.
In time step 0? Or
in time step 1, you have a vertex of degree 3. And in the underlying graph, it's degree 4.
Oh, thank you very much. Yes, you're absolutely correct. Thanks for clarifying. Yes. So here we have a degree 3, and there we have the degree 4. Yes, of course. And now the graph class that is particularly important for the talk today. This is the always star temporal graphs. So in every snapshot, we have a star with one center vertex. However, in the underlying graph, we don't have any restrictions on the pattern. These graphs appear in like sensor networks, where like one sensor sends out data to others, or in invitation structures and social networks. So they frequently appear also in real world data. There has been quite some work done by Egrida et al. And also by Ham et al. In the past on the sliding window temporal vertex cover. Most problems are known to be NP-hard. However, if we restrict the classes to underlying or always path, there are polynomial time algorithms. And also in the case where always degree at most B, there is, the problem remains NP-hard, but there are known approximations where we can get a D approximation in times Tm and a D-1 approximation in the time T squared, M squared, where T is the lifetime and M is the number of edges. What has been done in this work is we introduced new algorithms for the case of always star graphs, and particularly 2 algorithms that depend in their approximation ratio on the window size. And additionally, before the entire work on this problem has been done purely theoretical. And additionally, what we have done here is we implemented provided the first implementations and experiments for the exact and D and D-1 approximations, and see how they can be improved in practice. So a quick outline for the rest of the talk. We'll first go over how the always star algorithms actually work, and then we'll look at the experimental results and see how they perform in practice. So if we consider always star temporal graphs, it's quite obvious that in every snapshot we have a star. So the trivial idea is just include the star center of every time step where we have at least one active edge. And this actually leads to a very efficient algorithm because it is quite fast in time O of t with the approximation ratio 2 delta minus 1. Why 2 delta minus 1? If you think about, okay, what if nothing changes whatsoever? Then basically this algorithm just takes every star center whatsoever. However, we would only need one star center per overlapping window. So this is where this 2 delta minus 1 comes from. The question is now, can we do better than this? Because what we observe is, when do we don't we need to include the star center of a time step? So we do not need to include a star center when all appearing edges in this certain time step are covered in all of the windows by other star centers. So can we somehow do this? And we came up with the star all covered or just star all covered algorithm, where, yeah, this is the main idea, so to say. How does this work? In particular, we maintain this certain data structure here on the left. So we have a data structure that has window size on the top and number of edges on the right side. And basically what we do is in the form of ring buffer. So we have this toy example where we have 3 edges and 4 vertices, and we have want to solve it for a sliding window of size 3. So we have 5 time steps overall, so this means we have 3 windows. And basically what we maintain a flag for every star center to say, for now, it's available. However, if we look at the first window and the first edge, then we can see, okay, all in the first time step, all the edges, which is only 1, can be covered by other star centers. So we can exclude this vertex here, the star center in the first time step, and just use the star center in the third time step instead. And here for the second time window, we also need to include it because this edge here below cannot be covered by any other appearance in this window. So if we move now to the second window, so this was for the first window, and in the second window, we only have the time steps 2, 3, and 4. And as you can see, we use this ring buffer to improve memory. We don't need to do anything because in the first time step, there's no edge. And in the last time step, we also need to include the 5th star center because otherwise this edge DC would not be covered. Yeah, so this is the basic idea of how this algorithm works. And we can actually prove that this is a delta minus 1 approximation ratio that can be retrieved in time Tm delta squared time. What is the idea behind this ratio, just to get an intuition? If we have this very artificial instance here, we have just a very repetitive graph. So basically we have some sort of star in the first window, and then in the following windows, there are edge distinct subgraphs of this. So basically the idea is, okay, if our algorithm goes ahead and sees, oh yeah, this edge here can be covered by all subsequent time steps, so I don't need to include this first time step. So basically our algorithm would take all the green, would exclude all the green instances and take all of the red ones, while the optimal solution is the other way around. Therefore this ratio comes into place. So the question is now, how do these actually perform in practice? So what we did is we compared the exact, the star load coverage, the trivial star, and the D and D-1 approximations. So in terms of solution size, we can clearly see, so basically we just increase the maximal degree, and then can see in terms of solution size, relative solution size, all are pretty similar except for the D approximation, which is much worse. And in terms of running time, this is also very straightforward. We have the trivial algorithm to be the fastest, then the D-approx, the all coverage, and then the D-1 approximation. But now you can say, okay, but they have different approximation ratios because the star algorithms depend on the window size, while the D approximations depend on the maximal degree D. So what if we compare the edge case where actually the window size is much larger than the degree? But what we can see is that still, so we could expect here that theoretically we can create instances in this case where the D approximations would perform better. However, in practice, we don't observe this behavior as much. So what we can see here is that, the star or cover algorithm is still the one to produce the smallest size, except for the green one, which is the exact solution, while taking still much less time than the D-1 approximation. This is, in terms of intuition, quite clear because we use this additional intel that if we select one appearance, we will always choose the star center, while, for example, the D-1 approximation can always also choose some of the not star centers in the solution. In terms of larger instances, so now we didn't run the exact algorithms anymore because they take non-polynomial time here. What we could find out is that the star cover algorithm on geometric mean produced 40% better solution times in 200% better time and compared to the D-1 approximation algorithm. So these experiments you have seen so far were just performed on synthetic data because unfortunately there's no always star temporal graphs available. We only have arbitrary temporal graphs available. However, we wanted to still take a look on real-life instances from SNAP, and they're compared in particular the D-1 and D approximation algorithm. And it was actually a little bit surprising to see that because if you recall, the D-1 approximation computes a better approximation ratio, but also takes, I think, squared the amount of time compared to the D approximation. However, in practice, we observed that solution size was better as expected. However, also the runtime of the D-1 approximation was much better. This confused us a bit, so let's take a quick detour about why this happens and if we can fix something about it. So how does for now I just treated the D and D-1 approximations as sort of a black box, but let's take a little bit deeper look on what is happening here. So the D approximation algorithm was introduced by Agreda et al. And the main idea is that a single edge graph can be solved linearly in O of t time to optimality. So basically, in every time window, the idea is to choose the latest possible vertex appearance to cover it. So if we have our edge UV, for example, and it appears in time steps 2, 3, 4, 5, and 7, then we just take the first window and take the latest appearance, which is 3 to cover it. So we are good for windows 1 to 3. So the next window we consider is window 4. The latest appearance to cover it would be the 5, and so on. And then in the end, the idea is to repeat this for every edge and just combine the solutions of this. So this seems very fast, very simple, very efficient. However, the behavior we have in real-world graphs in particular is that they are often very, very sparse. So we actually need to maintain, so what we then proposed was an optimization where we maintain a data structure that not only just looks at every window, but we have to look at every window where the edge actually appears. And with this very small addition here that we added to the graph, to the algorithm, we can see a huge improvement. So the idea here is that the D approx minus S is the one we just improved, the simpler one that computes the exact same solution here, but has a huge runtime improvement compared to the D approximation algorithm by a factor of almost 260. And then we can actually see the observed expected behavior so that the D-1 approximation computes a better solution size, however, takes much more time than the D approx minus S algorithm. Okay, yeah, with this, I'm already almost at the end of my talk. So let's come to a quick conclusion. In this work, we provided the first experimental results for the sliding window temporal vertex cover algorithms. We introduced some practical optimizations, and we also proposed new approximation algorithms for the case of always star temporal graphs. If you want to check out the paper, the QR code here in the top should lead you to the archive. In terms of future work, it would be quite interesting to consider restrictions to other temporal graph classes, or in contrast, also use ideas to make it more general. And the other thing that would be really interesting, but also quite hard, is to actually experiment on always star temporal graphs that appear in real life. And what makes this a bit hard is to actually gain access to such data. In terms of what I'm doing, maybe a quick detour. I also worked on other things than temporal graphs, mainly dynamic graphs and parallel graphs. So the idea here is that we not only know everything in advance and try to compute an overall solution, as is done in temporal graphs. In dynamic graphs, we try to maintain the solutions under edge and node updates. And in general, my work is about bridging the gap between theory and practice, so make algorithms that have guarantees, but also are very fast in practice. So if you have any questions later, feel free to reach out. This is my email. But with this, thank you very much for your attention, and I'm happy to answer any questions. If there are any.
Yeah, thank you very much, Sophia. Can I ask a question?
Yeah.
So if I understand correctly, all the data sets that you used are from NEST, from the NEST library?
From the SNAP. So basically,
from the SNAP.
So two things. For the real world instances, only from the SNAP. For the always temporal graph, we used artificially generated ones because there are no real life instances.
So how did you do it? Like randomly, maybe?
Randomly, yes.
No.
So we did like Edish Rani model, and then also just randomly assigned time labels.
Yeah, thanks so much. I think David is also asking something.
Yeah, I was curious about the empirical evaluation and your experience of building the implementation. Were there packages that made this easier, or did you have to build everything from scratch?
So usually I build everything from scratch to also just build a data structure that exactly captures what we need to do. For example, here in this part where we need to include what is it that we actually need. So also in terms of cache cache misses and such. So we just create, usually we use something like edge arrays, and then make it very efficient in times O of 1 to access the time labels of edges. Because in my experience using libraries for this always takes more time than just using as small as possible data structure.
Okay. And the thing you developed then is a data structure that is specifically optimized for always star temporal graphs.
Yes.
So we are discouraged from taking this if we have other experiments with temporal graphs. It would be maybe not the best thing to adapt.
I mean, you could check out the data structure because it, unfortunately, I removed the slides in terms of time reasons where I was actually talking about the data structure itself. But you can check out the GitHub. So if you go to the paper, it links to a GitHub that is publicly available, where you can just look if it works for your application as well.